This is the video for day 17. Hopefully you're watching this before class on Wednesday. So today we're talking more about probability distributions. So when we first started talking about probability, we were saying that, hey, if we have some random occurrence, we can figure out how likely it is that a certain outcome happens. On Monday, we took a step back and said, all right, rather than focusing on one outcome, let's look at all of the possible outcomes and assign probabilities to each of those, and then think about that result, that collection of probabilities, as a distribution. Okay, so we're talking more about this idea today. We're going to be talking mainly about how we can manipulate this, how we can combine multiple distributions if, say, we have something happen multiple times. So this first part, we're going to be recapping some of the stuff that we talked about Monday, but I just want to make sure that we're all on the same page here. So we're going to have some variable x, which we're calling a random variable, which is representing all of the possible outcomes of some random situation. So in this case, we have, I would say, 5 possible outcomes. So our random variable x can be, in this case, 1, 2, 3, 4, or 5. And so we can figure out what the probability of one of these possible outcomes is. For example, we might say that the probability that our random variable equals 3, well, this might be something like 0.3. And maybe if I figured out the probability that our random variable equals 1, maybe that's 0.2, and so forth. So I can figure out all the different values and record them either in a table or in something like a histogram, where I'm recording the probability that our random variable equals a certain value. And this is certainly a weird thing to write. It's a weird thing to look at. The probability that x equals x certainly seems nonsensical, but the big X and the little x are talking about different things. The big X is our random variable. The little x is going to be one of these numbers, and the generic term is just going to be little x. So if we have a random distribution like this, it is often helpful to know, all right, well, what's the middle? What's the expected value? So the expected value, or the mean of the probability distribution, is going to just be, well, we can add up each of the possible outcomes times or weighted by its probability. It's less likely in this distribution that we get a 5, so the 5 is going to have a smaller weight because of its smaller probability. So in this case, what we would do is we would add up 1 times 0.2 plus 2 times 0.15, or what have you, 3 times 0.3, and add up each of those pieces. So we're summing each possible outcome times the likelihood that it occurs. Similarly, the variance is going to be found in the same way that we found variance when we were talking about sort of regular sample distributions back in the first couple weeks of class. So we are adding up the difference of each value, between each value and the mean, squared. So for each of the values, let's say 1, we're going to subtract 1 minus whatever we got for the mean, take that thing, square it, and then also weight that by the probability. So adding up all these things is going to give us the variance. Just like before, we're often interested in the standard deviation. So the standard deviation is the square root of the variance. We are going to sort of keep seeing this effect that standard deviation has a more intuitive sense. The scale for standard deviation is the same as the scale for whatever a distribution is. It makes sense to talk about measurements, talk about units when working with standard deviation. That said, a lot of math is easier with variance, and we will see this even more in the rest of today's class. All right, and then so to go through this example that, again, is something that we've already talked about, but the card game that we played on Monday, or that we talked about on Monday, we said that, all right, if you want to play the game, it costs $5 to play. The way it works is you draw one card from a standard deck of cards. If you happen to draw the Ace of Hearts, then you get paid $100, so big payout. But then there are some other smaller prizes that you can win. If you got an ace that wasn't the Ace of Hearts, you get $10. If you got any other heart, you get $5. But if you don't get any of those things, you don't get anything. Okay. So if we want to know the expected value or the average value for playing this game, well, we're not necessarily interested in how much prize money we get. We're probably more interested in the net effect, right? If I paid $5 and got $5 back, I didn't get $5. It was a wash. It was zero. So in that case, I would say that the outcome here, the net outcome here, would be $0. If I paid $5 to get $100, I would say that the net is 95. If I paid 5 to get 10, the net's 5. And if I paid 5 and didn't get anything back, I would say that's negative 5. Okay. So this is the column that we're more interested in. If we want to know the expected value, or if we want to pay attention to this distribution, we want to note the probabilities of each of these things occurring. The probability of, out of the 52 cards, drawing the Ace of Hearts is 1 out of 52. There are 3 other aces, and there are 12 other hearts. And then lastly, I believe there are 36 cards that under the system don't get paid anything. So we can find the expected value of x. Well, first off, let's make sure and make a note that x is the random variable representing the net result. So we can find the expected value of this random variable by just taking this weighted average. Well, sometimes we get plus 95, but that's only going to happen 1/52nd of the time. Well, sometimes we're going to get plus 5. That's going to happen 3/52 of the time, and so forth. Which I believe ends up being negative $1.35. So the average outcome, or the expected result of playing this game, is to lose a little over $1. Now, obviously, you can't ever lose $1.35 in this game. Like, either you lose $5 or you win some other whole dollar amount. But this is just talking about the average outcome. We can similarly find the standard deviation, which is going to be this big square root, which should end up being resulting in $13.80. So the standard deviation should be $13.80. So I want to point out that this number, obviously we can't possibly be a full standard deviation below the mean, right? That would be losing $15, which can't possibly happen. So there's sort of a running theme that these summary statistics, these numbers, aren't necessarily talking about real possibilities. They're just giving us a sense of the center and the spread of the probability distribution as a distribution. All right, so with this example, we could also take all this information and put it into a histogram, and then we can sort of visually see what the various outcomes are. And so this is just a rough sketch, but we can see that, hey, there is a very small chance that we get a very high payout, and most of the time we're going to be around here. This is probably actually even more extremely off that way, and these should probably be a little bit taller relative to this one, but you get the picture. So we could also label where the expected value is. So on average, we're losing $1.35, and so we could mark that on our histogram as well. All right, so then a question I have is, well, what if I play this game twice? What is the expected outcome then? What are the standard deviation, that type of thing? So, well, one thing I could do, one way to approach this would be to make a tree diagram. So there were 4 outcomes, and we can label each of the edges with the probabilities, and go from here. But the problem is that, well, actually with this particular example, this is certainly a feasible approach. Our tree does start to get very large very quickly. We have a total of 16 possible combinations of these things, which is a lot, but is sort of manageable. I'm sure you can imagine that if we were to say, oh, what if I play this 3 or 4 times, and maybe we had more than 4 possible outcomes, more than 4 things in our table, then working with the tree diagram might not be the best approach here. This is certainly a way to go, but if all we're interested in is what the expected value or standard deviation of this random variable is, if we're looking for the summary statistics of the distribution, we've got an easier way. The first thing I want to point out here is that expected value is additive. If we want the expected value of the sum of 2 random variables, well, that's just going to be the expected value of each of those variables added together. All right. And so what I mean by that is, if we were to take our original expected value, which is negative 1.35, and we said, all right, what if we were to do this twice? Well, it's just going to be 2 of these things added together. So if I were to play this game twice, the expected value of 2 of these, or put another way, the expected value of x plus x, is just going to be 2 of these things added together, which I believe comes out to negative 270. Right. So on average, each time we play this game, we lose $1.35. So if we play it twice, then on average, we would expect a loss of $2.70. Shouldn't be anything terribly surprising there. The next question is then, all right, what happens to the standard deviation? Right, so this 1380 number is giving us a sense of how spread out this data is. How much variance, how much variation is there in the possible outcomes that I get? Yeah, I know that each time I play, I lose 135, but, you know, is it the case that I'm like possibly gaining or losing $1 million? Or are we talking pennies, or what's the scale? This standard deviation gives us a sense of that. All right. So if we were to go and play twice, one question is, all right, well, what is this sense of scale? How does this standard deviation change? This is where working with variance actually makes our life a little bit easier. We can say that variance is additive, which means that the variance of doing something like this twice, so let's say one random variable plus another random variable, well, that's just going to be the variance of each of these things, each of these variables added together. So in this example, when we're working with these 4 possible outcomes, well, if the standard deviation is 13.8, then it must be that the case that the variance is just the square of the standard deviation. So the variance should be 13.8 squared, which I believe is 190.44. Weirdly becomes dollars squared, which is a weird unit. When we're working with variance, we're typically just going to ignore the units a little bit. So the idea is that if we want to know the variance for multiple instances, then the variance, in our case, of 2 of these games, well, that's just going to be twice the variance of one of them, which is 2 times, what did I say, 190.44, or 380.88. So the variance in our first example was 190, now our variance is 380, which is great, but this doesn't really tell me that much. Like, yes, this is a measurement. This is a sense of how much the variance is, how much variation do we have in the possible outcomes. But standard deviation intuitively just makes much more sense to me. It's on the right scale. It's talking about a measure for how spread out our possible outcomes are. So, yes, variance is additive, which is certainly an easy thing to remember. Another way of phrasing the same idea is that standard deviation, when we're talking about the standard deviation of two random variables added to each other, follows the Pythagorean theorem of statistics, which is just saying that, well, if we took each of these terms and put a square root over it, well, this first term becomes the standard deviation of these, then it's just what this next term is. So what I mean by that is the standard deviation of the sum of two is going to be the square root of the standard deviation of one of them squared plus the standard deviation of the other squared. And then, so again, in our example, we're saying that x and y are the same thing. We're just doing something twice. So the standard deviation of playing our game twice, the standard deviation of the outcomes of playing our game twice, is going to be the square root of the standard deviation of playing it once squared, which is the variance, which comes out to 1952. So the standard deviation of playing it twice is less than twice the standard deviation of playing it once. So each time we play this game, right, because there's a net loss, there's a house advantage, the expected value is negative, so on average, we're going to be losing some amount. That said, the standard deviation of playing this multiple times, if you're playing it more, there's going to be, in total, more variation. This seems like a somewhat silly example. It's a almost goofy card game that we're playing, but this is actually sort of the rough structure of things that crop up sort of in the real world a lot. Obviously, gambling, any sort of casino game, is going to have some sort of logic like this, where the house has some advantage, meaning that on average, each time this game is played, the player is going to lose a certain amount of money, but there's some variation so that, maybe they'll win. So obviously with gambling would be an example of this, but other examples crop in whenever we're talking about any type of insurance. Insurance is sort of hedging your bets against something bad happening. Whenever we're talking about warranties, like if you wanted to buy the extended warranty on something that you're purchasing, you're, in a sense, taking out an insurance. You're adjusting the various net payoffs, trying to guess what various probabilities are. So for those things like that as well, obviously you're trying to improve your expected value as much as possible, but you're also addressing this sort of idea of whether or not you are risk-prone or risk-adverse, right? If I just said, at the beginning, here is this game, do you want to play it? There isn't a hard yes or no answer. All right. Let's work through another example of this. So we're talking about insurance. The idea behind insurance is that you're hedging your bet against something bad that's going to happen. So let's say, and we're just completely making up numbers here, that 99 out of 100 times, everything's fine. Nothing bad happens. We're just sort of sitting normal at 0. But 1 out of 100 times, something really bad happens. There's a fire in your apartment, and it costs $1,000 to fix, or what have you. So we're going to say that we lose 1,000. Okay, so that's kind of a scary thing, like losing 1,000. That's a lot. So if an insurance salesman comes along and says, "Oh yeah, 1,000. That would be bad. How about this? If you pay me 15 now, then I'll cover the 1,000 if that happens." So in other words, no matter what, your outcome is negative 15. Cool. All right, so let's compare these options. Let's compare these two scenarios. In our first example, when we have no insurance, well, the expected value, which we could write E of x, we could also write mu, is going to be the weighted average of these things. So it's going to be 99 hundredths times 0 plus 1/100th times negative 1,000 should come out to negative 10. On average, we would expect to lose 10. Well, this is a very easy weighted average. We are just saying, hey, it's negative 15 always. All right. So why would we ever want the insurance? Well, let's look at the standard deviations. So on the left, we could calculate the standard deviation by saying, okay, how far away from negative 10 is 0? Well, 10 squared times the probability plus the same thing for this other term, and then all square rooted. In other words, the standard deviation of this, I believe, should be 99.5. Okay. Whereas on the right, the standard deviation is just 0. There is no variance, there's no variation, it's just always right at this mean. The reason people buy insurance is because they are risk adverse. They really don't want to deal with this minus 1,000. So because of that, they're willing to, on average, pay a tiny bit more, right? These insurance companies aren't doing this, out of the goodness of their hearts. They are on average getting, making money. But what they're doing is they're relieving the chance of a really bad outcome from the individual. So somebody who is risk adverse might be interested in taking out insurance on something by, in theory, paying a little bit more to reduce the variance. Somebody who's risk prone might be willing to pay more to get more variance, to have a higher standard deviation in the possible outcomes, as in do something like go to a casino. So these also aren't necessarily characteristics of a person. You wouldn't necessarily say, oh, that person is always risk adverse or risk prone. There are certainly circumstances where you would have insurance and to go to casinos. It's more about a specific situation. You might say that when it comes to this particular topic, this person is one or the other.